This week's content focuses on the sampling process and the audio file types that result. We will talk about the details of sampling, the standard values for certain parameters associated with sampling, and the audio file types that we use in today's marketplace. This week's content will focus on defining the details of the sampling process, understanding the essential terminology associated with digital audio files and file types, and discuss the digital audio marketplace and explore how we use and consume music in the 21st century. Understanding our place in the development of music and media is essential for modern music makers. We must understand the process of encoding and distributing music files. Last week we talked about sampling in regard to the ADC and the DAC in the recording and playback of digital audio. Because computers only understand data, or ones and zeros, in a collection of bytes and files, an analog audio signal or continuously varying electrical current must be encoded in a certain way so that a computer can understand it. This process is called sampling. Sampling is the process of measuring and encoding an incoming electrical signal into data. The sampling process is extremely important for digital audio. It must utilize a universal sample rate in order for this sound to be recorded and played back properly and in the same way. Our charts on the right show us how an analog wave shows its continuously variable state. On the right, we have its digital result when sampled at a certain rate, meaning the speed at which we take measurements or encode that particularly changing audio signal. Note that the faster the rate of this measurement, the more realistic our digital result will be. We must find a sample rate that is fast enough to create a digital replica that is realistic. Too slow of a sample rate will result in an unrealistic sound. The sample rate is the speed at which an incoming analog electrical signal is sampled or measured or encoded. The sample rate is measured in hertz or kilohertz, as is the frequency of any waveform. The sample rate defines the number of samples of audio taken per second. The higher the sample rate, the more information we have about the analog source signal, which results in a higher quality representation. The trade-off, however, is that a really fast sample rate generates lots and lots of measurements, creating lots and lots of data. If we are unable to manage all of this data, we must lower the sample rate. However, in order to capture audio in a particular way, we must increase the sample rate. Regardless, the same sample rate must be used for both recording and playback of a digitized sound. The Nyquist theorem states that because a periodic waveform has two sides or two halves, a positive and negative side to each cycle of its pattern, we must select a sample rate that is double the highest frequency we wish to sample. For example, to properly sample both the positive and negative portions of a 40 Hz wave, we must use a sample rate of at least 80 Hz, at least double the highest frequency we wish to sample. We can express this equation as 2 times the frequency. So if we look at our wave shape here, our sine wave as an example, if we only sample it at once every frequency or every cycle, we only sample half of the wave, or one peak. If we sample it at twice the frequency, we are sampling both at the peak and the valley of its wave. Therefore, we can construct or reconstruct a signal digitally more accurately. So the Nyquist theorem states that we must sample an incoming wave at least twice the highest frequency we wish to sample. Since the human hearing range is between 20 and 20,000 Hz, we must use a sample rate that is at least double the 20,000 Hz side or 40,000 Hz. The audio industry has established a standard sample rate for CD quality audio so that all compact discs and audio files are read properly anywhere in the world and on any device. Our CD quality standard and most common sample rate is 44.1 kHz. This odd number was arrived at as a compromise between a higher sample rate than 40,000 Hz, but also low enough so that we can capture enough audio or duration of audio on one compact disc. We can of course use higher sample rates, but that would generate too much audio to hold on any kind of disc. DVDs, for example, are able to hold way more audio, and so they use a higher sample rate. Aliasing occurs if we do not adhere to the Nyquist theorem. If we do not sample a signal at 2 times the frequency, according to the Nyquist theorem, aliasing will result. Aliasing is what we call a distortion of audio signal due to a sample rate mismatch. In the video realm, it is a interesting thing to note that we see this phenomenon sometimes on TV or in videos. Aliasing is visible when the wheels of a car or the propellers of an airplane or helicopter seem to be turning backwards, or not at all. This is a result of the frame rate or sample rate of the video being in sync, slightly lower or faster than the rate of spin of the spinning image. This results in an aliasing of the video. This kind of effect is also found in audio. If we utilize the standard sample rate, we will avoid this issue. Notice the mismatch in this example at the bottom. If we do not adhere to the Nyquist theorem and use a sample rate that is somewhat oddly in between, we get this sort of sample that creates a sound that is not quite the same. It creates a wave that is a distraction or an abstraction of the actual sound we're trying to capture. This link takes you to a demonstration of aliasing in the video realm. It is a great way to see aliasing in action. Bit depth is the amount of bits of information in each sample. It is related to the resolution of the sample. Bit depth in audio generally refers to the dynamic range of digital audio. Higher bit depth files will have a bigger spectrum between soft and loud sounds and will then therefore be more realistic sounding. We can think of bit depth quality also in video. Higher bit depth in video results in the ability to use things like three-dimensional video or to do more with our video to make things look more realistic. The audio industry established a standard bit depth for CD quality audio as well, so that all CDs are read properly anywhere in the world. Our CD quality standard bit depth is 16-bit. If we look and compare these two graphs, the 16-bit example has more values per sample. This sample and this sample and this sample all have more information to them, allowing for us to encode more details. This 8-bit sample rate really also is giving us a lot fewer information, even though the sample rate is the same. So the depth of the information per sample is what we're measuring with bit depth. Now that we've discussed sample rate and bit depth, we can talk about the compact disc quality standard. CD quality standard is still utilized, even though CDs are not as widely used. The compact disc was developed at the dawn of digital audio in the early 1980s, late 1970s. They are still used today as ways to measure original CD quality standard audio. Just like the development of media in the past, the CD came before streaming services, and therefore sets the standard for CD quality audio. Bit depth and sample rates must be standardized across the industry so that all devices and media work properly together worldwide. We must know the CD quality standard for bit depth and sample rate in order to be successful in this industry. This generally means that a CD purchased in any music store in any country across the world can be placed in any CD player and have a successful playback without aliasing or any other types of mismatch. The sample rate and bit depth for CD quality audio is 44.1 kilohertz for its sample rate and 16-bit bit depth. These standards will result in a file that is approximately 10 megabytes per minute of audio. This is useful to know, especially when we start talking about compressed audio files. This chart shows an array of values for standards, and if we look at our top row here, it says that we have a 16-bit 44.1 CD quality audio when stereo, gives us about 10 megabytes per minute. We can increase these values, of course, for higher standards. For high def audio, we have 24-bit 96 kilohertz, 24-bit 48 kilohertz, but that produces files that are much larger in size. We need to think about or consider the size of the file that we're generating in comparison to the audio quality that we wish to have. Audio files intended for physical media such as CDs and DVDs and computers and consoles are generally WAV and AIFF files. These files are considered to be of full audio quality, and they can be found on commercially produced compact discs and DVDs. Audio files, however, that are intended to be distributed over the internet need to be compressed. The network that we use for cell phones, for computers, Wi-Fi, those are all very great, but they cannot allow the distribution quickly enough of audio files in order for them to be played in real time or to be streamed. Also, it is very, very hard to email a WAV file or an AIFF file or to upload it to the internet. Audio files must be compressed in order for them to be successful in today's marketplace and to be distributed over a network. This means that the original WAV file has to be decreased in size in order to make it small enough to send over a network. Audio file compression can be categorized as either lossless or lossy. Lossless compression means that the file size is reduced without discarding audio data. Lossy compression means that audio information is discarded for the sake of smaller file size. The most common compressed audio file type that we use is the MP3. The MPEG format is in many generations. The fourth and fifth are out today, but we generally consider them to be called MP3s in general, and it is a standard compressed audio file format. Although it is lossy, the MPEG algorithm can sound or be perceived as lossless. However, other file formats do exist. FLAC files, for example, are truly lossless, but they are less commonly used. Compressed audio files are reduced by 90%. 90% of the data of a WAV file is discarded generally to create an MP3. However, it is interesting to compare the audio quality of an MP3 to an AIFF or WAV file. The trade-off is that instead of dealing with 10 megabytes per minute, they are only 1 megabyte per minute and easily streamed or emailed over a network. In today's marketplace, we need to consider that trade-off when we consume or listen to audio. Today, most people stream media content. Streaming means that any media content, live or recorded, is delivered to computers and mobile devices via the internet and played in real time. In today's marketplace, it is more likely that we stream audio content rather than purchase a newly released album on a compact disc or even a record, which is analog. The compact disc that we would purchase commercially released is of uncompressed audio. Services like Spotify and Apple Music allow us to stream content on a paid subscription basis. However, we do not ever own a tangible album in this case. In order to listen, we must pay for that subscription and own it temporarily while we stream it. This is the trade-off. Streaming services offer audio quality that is not nearly as good as a compact disc. However, with streaming services, we have the ability to subscribe and access virtually any recording at any time, on demand. We must consider this trade-off when we consume our audio. Would we rather have a tangible disc to own and to listen to at highest quality and at high quality settings? Or do we want convenience with a lower audio quality? This trade-off is becoming slimmer and slimmer these days as streaming services provide higher and higher quality compression. Streaming can be useful for emerging artists as well. It is increasingly easier to post new works and to distribute them on the internet. This is often free to do and is essential to promote yourself as an emerging artist. Bandcamp and SoundCloud are examples of two services that host compressed audio files for users for free. And if I'm not mistaken, Bandcamp actually uses WAV files instead of compressed audio. We will create Bandcamp or SoundCloud accounts in this course in order to host our newly created audio.